Welcome you all to another lecture series on YouTube. Our YouTube channel, if you have followed, is Inquisitive Engineer, and it has been a few days since we posted our last video, and our last video was related to the response spectrum analysis. We will be starting a new video lecture series from today, and that will be related to the design of steel truss shed using IS code method. We have started and we have completed two lecture series on our YouTube channel. One was seismic resistant RCC building design of a residential building, and another was the response spectrum analysis, which is the dynamic analysis method. We have also started, and I think we have done 2 or 3 videos regarding the detailing of RCC structural members. We will also continue with the videos in that series in our future. For today, we will be having an introductory class to the design of steel truss shed. We will look at some introductory portions related to the design of this steel structure, and we will see at the end of our introductory video today what we will be learning in this lecture series. So before beginning with the introductory class, uh, in comments of my previous videos of other lecture series, also many of you have asked for some related presentations, some related quotes, and I haven't been able to reply to those comments and send you the relevant quotes and documents because of some constraints. So if you want all the related quotes, all the related Excel sheets, or my presentations regarding our other two lecture series that we have completed in our YouTube channel, I request you all to please comment with your email address on the comment section for this introductory video lecture. I will be posting this introductory video lecture today itself on YouTube, and you can comment with your email address, and I will provide you with all the documents and all the codes, Excel sheets that I have. So saying that, I want to begin with our today's video lecture, or today's our introduction. And I have written here introduction to pre-engineered building and design of truss shed. Before beginning with the design of truss shed, let's see what is a pre-engineered building, or what is a PEB structure. A pre-engineered steel building. I have written steel building because generally our pre-engineered buildings are made up of structural steel. So a pre-engineered steel building is a modern technology where the complete design is done at the factory and the building components are brought to the site in completely knocked down condition, and then those components are fixed or jointed at the site and raised with the help of cranes. So one of the prominent features of pre-engineered building is that, or pre-engineered structure is that, the a single person or a single entity is responsible for both the fabrication of the structure as well as the erection of those structures in the site. All the elements or all these major components such as frames, column, rafter, purlin, etc. that are used in pre-engineered building, those are designed and manufactured at the factory itself, and then those manufactured portions or manufactured components are brought to the site where the erection is done. If we take any RCC structure, for example, in those, while building those structures, what we bring to the site are only the basic materials. For example, we bring cement, we bring fine aggregates, coarse aggregates, water to the site, and then those aggregates are mixed, placed, and compacted using some proper techniques in the site itself. But in case of our pre-engineered building, all the required components are manufactured at the factory itself, and they are brought to the site and then fixed or jointed at the site only. An efficiently designed pre-engineered building can be lighter than the conventional steel buildings by up to 30%. It is because our specifications for construction of pre-engineered buildings are already fixed. The purpose for which that pre-engineered building or that structure will be used in the future is already fixed. And also the design methodology and all the loads acting onto the structure are already determined beforehand, before the fabrication of those components. So what is possible in such cases in which our design methodology, in which the loads coming onto our structure are already fixed, is that a proper component can be designed. We do not need to design any heavier component in which large amount of steel is used, contrary to what is exactly needed according to the use of such structures. So if we are able to design such PEB structures efficiently, then they can be lighter than the conventional steel structures by up to 30%. So the major components of a PEB includes the primary components are main frame, and our main frame is composed of, if you look at the picture given alongside here, our main frame is composed of a steel column and then a steel rafter. So the primary components are these steel columns, steel rafters, and other secondary components include purlins and grids. If you see here, these horizontal members supported by the rafters are the purlins, and these purlins are used for supporting the roofing seats or seatings. And grids, these horizontal members which are connecting these two columns here, these are the grids. EV struts. EV struts is not shown in the diagram here. Bracings. Our bracings can be either plan bracings, which are given on the plan or on the roof of our PEB structure, or it can be elevation bracing, which is shown as cable bracing here, or these also can be sag rods. Seating and cladding. Our seating is supported by the purlins, and our seating can be of different materials, for example galvanized iron sheets or asbestos sheets or even UPVC sheets and other accessories. So the main components of PEV are the primary components, which include the main frame and all the other secondary components. So PEV structure or these steel truss structures are very popular nowadays because of the relative ease of construction and also the relatively lower cost is compared to RCC structures. Where are these structures used? These are used to make or to build factories, warehouses, workshops, or even office building, schools, community center, etc. So these PEV structures are gaining a large popularity in these days. So one difference that we have to know between two types of structure is one is pre-engineered building or PEV structure and another is prefabricated building. So what is the difference between pre-engineered and prefabricated building? As we talked about before, in pre-engineered building, the specifications or the purpose of our structure is already fixed beforehand. So that means that the loads coming onto such structures are already defined before the fabrication of those components, and an efficient design is performed based on the use of our structure or based on the loads coming onto our structure. Our fabrication of the components is based on that design, and that fabrication is performed at the site itself. And that fabrication is performed in the factory conditions, and those components are then brought to the site for fixing and jointing. That is pre-engineered building. As the name suggests, pre-engineered. But in case of prefabricated buildings, only the frame components or only the components of our structure are fabricated at the site. For example, if we are constructing a two-story steel building with truss at the top, and if we are thinking of using some prefabricated wall panels for as exterior walls and interior partitions and using some UPVC doors and windows, then all those components, they are manufactured at this factory, but the specifications or the design is not fixed at the factory itself. The design is performed by an engineer or performed by the client, and based on that design, the factory separately manufactures all the components. So that is the difference between pre-engineered building and prefabricated building. So this was just an introductory slide on what is pre-engineered building. Our design will be related to a steel truss, which is some kind of pre-engineered building, although not totally, because uh, the design, although those steel structures or steel frames are manufactured at the factory, the design is not done by the factory itself. It is just somewhat related to pre-engineered buildings. So I just wanted to include an introductory slide. So if you see here, here are two figures of pre-engineered building. One is just a diagrammatic representation and another is a real life structure. I haven't, I just want to acknowledge the source. I derived these images from Google Images, and I selected these images and uh, pasted onto my slides. I just want to acknowledge the source from wherever these pictures I have derived. If you see at the figure here, this is just a diagrammatic representation of a pre-engineered building. You can see here we have vertical columns, we have rafters, and we have purlins here, we have roof seating, we have wall grids, we have plan and elevation bracings, and other components like gable end bracing or E-purlin or wall grid. This is just a diagrammatic representation, and here is an example of PEB structure in real life. These are the columns, these are the rafters you can see here supporting the purlins, and these purlins are in turn supporting the roofing sheet, and then we have some sag rods here. These are acting as elevation bracings. So this is an example of a PEB structure or pre-engineered building. So now we come to the design of a roof truss part, which will be the main content of this video lecture series. Similar to pre-engineered building, roof trusses or the steel roof trusses or buildings with steel roof trusses are gaining popularity these days because of various reasons. And we can construct these roof trusses either on some reinforced concrete frames, that is reinforced concrete columns. These roof trusses can be either supported on reinforced concrete columns, or this can be supported on masonry walls or on steel columns itself. So we will be seeing, or we will be studying, we will be discussing the design of steel truss, steel roof truss supported on steel frames in this lecture series. So roof trusses are the choice for long span floors and roofs of a multi-story building, industrial building, cinema halls, malls, and stadia. In cases where we need large open area, then in such cases generally, although our walls may be masonry and our supporting columns may be either RCC structure or masonry walls, our roof covering will be the trusses itself. So these trusses are the choice for floors and roofs with very long span. For small span industrial building bends, the choice may lie between a small beam and a roof truss. For example, if this is our span of any building or any structure, then we have two options. Either we can connect these two columns using a beam, or we can design a truss for the roof of this structure. The trusses consume much less steel as compared to the beams for the same load and span. However, the fabrication and erection cost is more. Although these beams may be very easy to construct and the construction cost of these beams are less, but sometimes these beams may not be sufficient because of the long spans in which we use or we design the steel roof trusses. So these steel roof trusses, they consume less steel and hence are economical as compared to the beams, but the erection cost, the fabrication cost of these roof trusses are generally larger compared to the beams. So while designing a structure, we have to be careful and we have to be prudent in choosing which type of load resisting system, or which type of structural system will we prefer to use. So theoretically, roof trusses are supposed to resist in-plane loading by developing axial forces. This we have, or we know from our structural courses, but in reality some shear and moment is always there at the joints which are neglected. So what we learned in our sorry what we learned in our structural courses is that if this is a truss member, a triangular truss member composed of three elements, and suppose that a gravity load or a load in the vertical direction downwards is acting at this joint, then under the influence, if we suppose that these two joints are restrained here, under the influence of this vertical load, what happens is that this joint moves downwards here, whereas these two joints on the left and right, they move outwards, somewhat like this. So you see here, if you consider this triangulated truss, under the effect of this vertical force, this joint at the top moves downwards, whereas the joint at the bottom, these two joints move outward. As a result, what happens is that if we say this is A, this is B, and this is C, our member BC will be in tension, because we can see that as the joints move outward, there is a tension force being developed in this member BC, whereas our members AB and AC will be in compression under the effect of this vertical force. So theoretically, these roof trusses just resist the external loads by developing axial forces, and these axial forces can either be tension or compression. So I'm talking about structural behavior of trusses, just a small introduction. We saw that there is either tension or compression in the component members of the truss. But what happens in reality is that some shear and some moment forces is always there at the joints which are neglected. When we are performing, even when we are performing manual calculations of truss forces, we neglect all kinds of secondary stresses. In analyzing a roof truss for determining the distribution of internal member forces, it is universal practice to assume the members to be pin connected. That is, at the joints A, B, C, theoretically we consider, or we should make it theoretically, what we consider is that these joints are pin connected. And that pin connection in reality is seen or is assured by using a single bolt at each member end. If we are connecting these two members at joint B, or these two members at joint C, or these two members at joint A, if we are connecting all of these two members using a single bolt at each joint, then we can assure that our structure, or we can exhibit that our truss structure will be pin jointed. However, is this the case? Do you see our trusses being built like that in reality? No, this is never the case for a roof truss. That members, or those members, are rigidly bolted. That means they are bolted with more than one bolt, or even welded to gusset plates or to each other at the joints. Instead of using a single bolt for connection, we either use multiple bolts or we weld those two connecting members. And that because of that use of multiple bolts or use of welding for connection, that introduces rigidity at the joints between the ends of the members. And these end moments, because of the rigidity, give rise to the secondary stresses. So consequently, what happens is that these members are subjected to moments in addition to axial force, generating secondary stresses. And these secondary stresses can be computed. If we want to compute manually, then those secondary stresses can be computed by indeterminate structural analysis, but we are not concerned with that at the moment, because Usually, if we do manual calculations, the amount of work involved or the amount of effort required for that computation is very large, and that amount of work is not justified for the analysis of an ordinary roof truss. So we just neglected secondary stresses. So that we have discussed a little, or we have touched a little upon the structural behavior of these trusses. So how do we select the truss type? In reality, we have to perform analysis and design for the selection of truss type for our structure, but there are some common truss types that can be used based on the span of our structure. For example, if you see at the diagram on this left hand side, we have the king post truss for spans up to 8 meter, queen post span up to 10 meter. We have hoe truss with 4 and 8 panels and for spans up to 6 meter to 30 meter. Similarly, we have plat truss, fink or French roof truss, and other compound trusses also. Similarly, we have here one north light roof truss. This north light roof truss, we generally see these trusses being built in daily life, and these north light roof truss are particularly suitable when we have to make proper provision of lighting in our structure. And similarly, we have some trapezoidal shape truss like this quadrangular truss, and for if the span is very large, then we can use this circular trusses or these curved trusses for large span also. So the selection of any type of truss depends on our structure itself. Let's see here. Roof trusses may be either pitched truss or a parallel chord truss. All of these trusses are pitched truss or these are sloping trusses. And these sloping trusses are particularly suitable or needed when we have to make sure that the loads of the rainfall or the snow coming onto these trusses are, or the loads coming from rain and snow on these trusses are properly diverted or properly channeled into the ground or into any other places. So these pitched trusses are generally provided in industrial buildings. For very long span, pitched roof trusses have trapezoidal configuration, like this quadrangular truss here. So we see that the primary factor governing the selection of truss is our span of the structure. Slope of bottom chord may be kept equal to half the slope of the top chord for optimum design. So if these rafters are our top chord, then this is our bottom chord. If these rafters are our top chord, then the beams at the bottom are our bottom chords, and it is generally seen that if you look here, for all of these trusses, the bottom chord have no slope, they are just horizontal. But if we have a large span, then the slope of bottom chord can be made greater than 0 degree and kept equal to half the slope of the top chord for optimum design. Chord members of trapezoidal configuration that are adjacent to the supports experience less axial forces as well as secondary stresses. This is also related to the nature of our trusses. What it says is that, for example, in this truss here, if we have supports here and here at the ends, then these chord members, these inclined members or these vertical members near the support experience less axial forces as compared to the members near the center of the truss. Trusses with smaller depth result in larger member forces. So depth means this is the depth of our truss. Another thing or another factor for selection of truss type is also the depth of the truss. Steep pitched roof are avoided as these will be subjected to greater wind pressures. We will talk about wind pressures or wind load coming onto our trusses in our upcoming slides also. So we have to make sure that the sloping or the slope of these pitched trusses are neither very less such that the rain or the snow load coming onto these trusses they cannot be diverted properly, neither or nor this depth of the trusses should be so large, because larger the depth of these trusses, the experience or the effect of the wind forces will also be greater. And here is one point to remember: for economic spacing of roof trusses, the cost of trusses should be equal to twice the cost of purlins plus the cost of roof coverings. This is just to check the spacing of trusses. This does not give us the final spacing of trusses. This is just to check the spacing. Now let's see the loads coming onto our roof trusses. We will see that there are four major types of We will see that there are four major types of load coming onto a truss, roof truss. One is the dead load, live load, snow load, and wind load. So the dead load include the load of roofing materials. Load of roofing materials, purlin, truss, and any bracing system that may be present on the roof of our truss. So these purlins and other bracings, these elements of our roof truss can be modeled into our SAP model or our ETABS model or in any software. So we do not have to separately consider the dead load for these structures or for these components, including purlins and bracing, if we have modeled those elements into our software model. But if we haven't modeled them, then we have to consider the loads coming on from those components onto our rafters and onto our frames. The weight of purlins is known in advance as these are designed prior to trusses. Yes. The dead weight of the trusses may be assumed to be equal to 10% of the loads on the truss. So this is just assumption here. Here we have an empirical formula for the approximate dead weight of roof truss in Newton per meter square. That is span divided by 3 plus 5 into 10. This is just an empirical formula. And the weight of the bracing may be assumed to be 12 to 15 Newton per meter square of the plan area. So these three here are just some empirical formulae and just some assumptions here. We will do the modeling of our truss in our software, and for those components that we have modeled, we do not need to care about the dead load of those modeled elements because the dead load will be calculated by the software itself. Here in IS 875 part 1, this IS 875 part 1 gives us the dead load for seating, and that seating is our protected galvanized steel seats. These are the normal, or these are the most commonly used roof materials or seating materials in case of trusses, and this IS code part 1 gives us the dead load for these roofing materials here. You can see that our roofing materials are divided into 4 classes according to IS code 277, and these classes are based on the depth of corrugation or the pitch of corrugation. So you can go to this IS code, you can download this 277 IS code and see how these corrugated or how these galvanized steel sheets are divided into different classes. Under each class also, the nominal thickness of the galvanized sheet varies. For example, under class 1, the thickness of our galvanized steel varies from 0.63 mm to 1.60 mm. Similarly, under class 2, class 3 and class 4. And then the loads for these roofing sheets are given in kilonewton per square meter and kg per square meter here. So based on the type of material that you will be using in your structure, we can select the dead load of roofing sheets from this table. In number 39 of this IS 875 part 1, we have the dead load for galvanized steel sheets. The second load coming onto our roof truss is the live load. This live load, we have also discussed it many times before. This live load value is given in IS 875 part 2 code. What it says is that if we have flat slopes or if we have flat roof or sloping or curved roof with slope up to and including 10 degrees. For slope up to 10 degrees, if the access to the roof is provided, then the live load will be taken as 1.5 kilonewton per meter square. And if the access is not provided except for maintenance, then the live load will be 0.75 kilonewton per meter square. So this conditions is for the pitched roof or sloping roof with slope less than or equal to 10 degrees. But if the slope is greater than 10 degrees, what we have to do is that for roof membrane sheets or purlins, our live load will be 0.75 kilonewton per meter square less 0.02 kilonewton meter square for every degree increase in slope above 10 degrees. That means, suppose the slope of our roof is 15 degree. Then for this 15-degree roof, our live load will be this 0.75 minus, so 15 minus 10 degree means 5 degree, so 5 into 0.02, 0.02. So you get this to be 0.65 kilonewton per meter square. So these are the values of live load. I will repeat again. For slope up to and including 10 degrees, if the access to the roof is not provided except for maintenance, then our live load will be 0.75 kilonewton per meter square. If the access is provided, double 0.75 into 2 means 1.5 kilonewton per meter square. And for slope greater than 10 degrees, we have to subtract from this 0.75 kilonewton per meter square 0.02 kilonewton per meter square for every degree increase in slope from 10 degrees. So this is about live load, and another type of load coming onto a roof truss is the snow load. So for the application of snow load, about how snow load is calculated, you can see IS code 875 part 4. So what this code says is that roofs should be designed for actual load due to snow or for the imposed load specified in IS 875 part 2, whichever is more severe. That means we do not have to consider both snow load and live load in our single structure. We do not have to consider both types of load simultaneously or parallelly. What we have to do is that we have to calculate the value of both snow load and live load, and we have to design for the critical load. That means for that load which value is higher. If snow load is greater, then we should consider snow load, or if the imposed or if the live load is greater, then we have to consider live load. And it is evident that snow load should be considered for design if the structure is situated in an area where the roof is subjected to snow. So this IS 875 it gives us a formula in 3.1 for the minimum design snow load on a roof. What it says is that the minimum design snow load on a roof or any other area above ground which is subjected to snow accumulation means it is given by the multiplication of these two factors, mu into S naught. This mu is the shape coefficient, and this shape coefficient is different for different types of roof. It is given in the same code itself. And then S naught is the ground snow load in pascals, that is ground snow load in Newton per meter square. So this is how you calculate snow load. We will not consider snow load here in this lecture series for us. And finally, the fourth load acting on our I missed one slide here. Let me just see here. Okay, I think I deleted one slide here, so I will just discuss it. Fourth load, or one of the most important load, is the wind load. Since our steel structures or our pre-engineered buildings are lighter in weight also, wind load will have a prominent impact on those structures. And one of the chief impact of wind can be that first, the wind will have a greater effect on our roof covering or on our seating materials because of the pressure that it develops both externally and internally also. And another is that if we do not design our foundations properly, then one of the impacts of the wind loads can be the uplift of our structure from the foundation itself. So this uplift force is also one of the prominent impacts of wind forces on our steel structure or on our pre-engineered buildings. So we will be looking in detail. One of the aspects that we will cover in detail in this course is the calculation and the calculation of those wind loads, and then application of those wind loads onto our model in our software. We will look in very detail, or we will look in minute detail about the application of wind load. So there are we discussed four different types of load acting on our roof truss: dead load, live load, snow load, and wind load. And finally, before ending this first lecture, let's see what will be covered in this lecture series. So our lecture series name will be Analysis and Design of Steel Truss Shed in SAP 2000 software using IS code. I will be doing this lecture series on SAP 2000 software. We will also learn a little about the use of SAP 2000 software. It is not much different from ETABS. Both softwares are the product of CSI itself. So SAP is a more generalized software and is used for the design of various structures besides building. ETABS is only for the analysis and design of buildings. So we will be using SAP 2000 software in this lecture series. First, before beginning with the modeling of our steel truss in SAP, in our next lecture we will look at wind load calculation using IS 875 Part 3 manual calculation. We will look first at this wind load calculation in detail, so that when we are doing analysis and design in our software, then we do not have to stop for learning the basic concepts during that process. In software, we can just apply the related factors or related values of wind load itself. We will first look in detail about wind load calculation. Then the remaining workflow is the same as we saw for the building design in ETABS. We will model the steel truss shed in SAP. We will define different materials, different load pattern, load cases, and load combination. We will see about calculation of dead load, live load, and wind load, if any remain. We will assign the releases and supports to our structure. We will analyze the steel structure. And then finally, we will perform the design of that steel structure as per IS code. And at the end, we will check for results, including the material takeoff, that is, including quantity estimation. So these are the things that we will cover in this lecture series. In our next video lecture, we will see wind load calculation using IS 875 Part 3, latest revised version, that is of 2015. So this brings us to the end of this introductory video lecture. We will meet again soon. Thank you.